We're going to look now at a transformation. So remember, a transformation is a function. Okay. It's a function a little bit different from the ones we have seen so far, though. Okay. It's a function that actually works on matrices. Okay. So what we do is we start from an invertible matrix P, and we're going to consider the transformation done on square matrices of the same size as P. Okay, which takes a matrix A and changes it to the matrix P inverse times A times P. Now, from general algebra, you might say this is a silly transformation because P inverse and P should cancel with each other, and therefore we just get back A. Not quite. Remember that matrix multiplication is not commutative, and we're not dealing with diagonal matrices now. Okay, so we're just dealing with regular square matrices, and therefore P inverse and P, well, there's no guarantee that they're going to cancel at all, and so P inverse AP in general is going to be something different. Now, this transformation is always also a very nice transformation. By the way, it's called a similarity transformation, and it is also a very nice thing to work with. Why? It has lots of properties. Once again, I'm going to list what those properties are. We may review them in class if you so wish, and we're going to look at the proof. Okay, but each one of these statements I'm going to make, each one of these exhibits these nice properties, can be proved very easily, and I strongly encourage you to have a look at have a try at proving them. So, first exhibit. Exhibit 1 is a transformation like this is linear. Remember what that means? It means that if I look at the image under this transformation, under this function of a linear combination, I will end up with the same thing as by taking the corresponding linear combination of the images. So whether I combine A and B through H and K before I transform them or after I transform them, I end up with the same thing. Now, this is not a proof, okay? I'm just claiming that. So what you need to do is you need to prove it on your own. See if you can figure out on your own how to show that this is true. All you need to do is look at the definition of this transformation, what this transformation does to a matrix, and then use everything you know about matrix products and inverse matrices and so on to figure out if in fact that is true or not. Exhibit 2. This transformation distributes products. Ooh, what does that mean? Well, what that means is that if I consider the image of a product of two matrices, what I end up with is the product of the two images. Remember earlier on we saw that the determinant of a product is equal to the product of the determinants. Well, this happens as, this is true as well in this case. So the transformed of a product is equal to the product of the transformed. Again, I'm just claiming that. You have now to stop and find out on your own, use some suitable arguments. Again, use the definition of this transformation and properties of matrices that you know to show that this is true. None of these proofs, again, are very long. Each one of them is one line long, okay? But what you have to do is, as usual, just go through the thinking process correctly. Exhibit 3, DP preserves determinants as well. What does that mean? It means that if you look at the determinant of the image of A, so that P inverse AP, that turns out to be exactly the same as the determinant of A. So by applying this transformation, we go from one matrix to another one. Both the beginning matrix and the end matrix have the same determinant. Again, prove it. Very, very easy. This is probably the shortest of the three I've shown you so far. Next, Exhibit 4. DP preserves the characteristic polynomial. Okay, so what I want you to do is, again, just pause here again, think about what the characteristic polynomial does, and then what you have to ask is, once again, is it true that the characteristic polynomial of the transformed matrix is the same polynomial, just exactly the same as the characteristic polynomial of the original matrix. Okay? So I'll leave that to you to even write down what that means. So the translation from the words to formula, and then prove it. Okay? Again, once again, don't just rush through this class, through this lecture. Stop every time I tell you to, rewind if you have to, but make sure that you prove each one of these things. Then in class, we're going to analyze a little bit more whatever aspect of these proofs is unclear to you. One more. Exhibit 5, this transformation preserves eigenvalues. Well, this is kind of easy. If it preserves the characteristic polynomial, remember the eigenvalues are the solutions of the characteristic equation, the roots of the characteristic polynomial. If the characteristic polynomial is the same, the eigenvalues are going to be the same, right? So nothing to prove here.